everyone. I think you should see my screen, right? You still see it?
Yep.
Okay, good. All right. So as you already heard, my name is Vladimir Khorikov, and today we'll talk about unit testing best practices. Just a couple of words about myself. As you also heard, I have a book. It's called Unit Testing Principles, Practices, and Patterns. And I also have several courses on Pluralsight. They are mostly about domain-driven design, but I also have some about unit testing. All right, so the agenda for this talk is going to be the following. We'll talk about how to measure the effectiveness of a test, then we'll talk about how to put this knowledge to practice, and how to write effective tests. And then we'll discuss the topic of mocking, when you should and when you shouldn't use mocks. So when we are talking about ways to measure test effectiveness, unit test effectiveness, unfortunately, there is no good automated way to do so. And when we're talking about that, we usually think about test coverage or code coverage. They are synonyms. And test coverage is not a sufficient metric for these purposes. And that's because test coverage is a good negative indicator, but it's a bad positive one. And what do I mean by that? If you have some low coverage number for your tests, let's say anywhere lower than 40% or 50%, then it's a good sign that you don't test enough. You don't have enough tests in your project. But even if your test coverage metrics show you some high coverage numbers, 90% or even 100%, it doesn't necessarily mean that the quality of your tests is good. So it's not, and because of that, it's not a sufficient metric to measure your test effectiveness. The only way to measure that, to do that, is to evaluate each of those tests separately. That's unfortunately the only way I know of how to do that. So how to do that exactly? There are 4 components that will help you with that, and they are protection against bugs, resilience to refactoring, or as I call it in the book, resistance to refactoring, but I like the word resilience more. And then we have fast feedback and maintainability. Let's discuss all 4 of them. We'll start with the second 2 because they are easier to describe, and then we'll go back to the first 2. So fast feedback. Fast feedback is pretty much self-explanatory, and it shows you how fast your tests execute. And it's important because the faster you get the feedback from your tests, the faster they find you bugs, the less time you spend on moving in the wrong direction. And also, the sooner you reveal a bug in your project, the easier it is to fix that bug. So for example, when you find a bug during development, then it's virtually free to fix. You just need to change the code and that's it. And if you find the same bug in QA environment, then it becomes an order of magnitude more difficult to fix because you will have to communicate with the QA people. You will need to deploy a new version and they will need to retest it and so on. And the very same bug that you found in QA, if it goes to production, then it becomes even harder to fix, another order of magnitude harder to fix because of all these additional frictions that you need when you fix bugs in production. The 4th component, the maintainability component, consists of 2 subcomponents. The first one is how easy it is to understand the test. And the second subcomponent is how easy it is to run this test. And the first subcomponent, how easy it is to understand the test, is a function of the size and the clarity of the test. So the smaller your tests, the easier it is to understand that test and easy it is to maintain it moving forward, to change it, update it, and so on. And of course, the clarity of your tests also matters because, it also code, and the clearer this code is written, the easier it is to understand this code. The second subcomponent, how easy it is to run the test, is basically a function of the number of out-of-process dependencies that this test works with. So, for example, if your test works directly with the database, then you will have to keep that database operational in order to maintain your test suite. You'll have to reboot it at times. You'll have to make sure that it's reachable through the network and so on and so forth. The best tests in this regard, in terms of this second submetric, are tests that only execute in memory. They don't reach out to any out-of-process dependencies. So these were the third and the fourth component. The first component is protection against bugs. And this component, it consists of, it depends on the amount of code that gets executed by the test. And it's important because the more code your test executes, the higher the chance that the test will reveal a bug in this code. And also, it's not only the amount of code, but also the importance and the complexity of that code that you need to keep in mind. And that's because the most severe bugs, the most critical bugs tend to appear in your business logic or in some complicated, overcomplicated code. And so you need to make sure that you cover those parts of your project the most. And also, it's not only your code that matters, but also the code that your code integrates with. It's the external libraries and systems, such as, let's say, frameworks or payment systems, and so on and so forth. And it's important to test not just your code in isolation, in a vacuum, but also it's important to test how your code integrates with those libraries and external systems. So that was the first component of a good test. The second component is resilience to refactoring. And this component depends on the number of false alarms that your tests raise after you refactor the code under test, the underlying code. So the more your code resilient to refactoring, the fewer false alarms it will raise. So a false alarm is the same as false positive and the same as false failure. They are all synonyms. So why this second component is important? That's because false positives or false alarms, they affect your ability to refactor your code. And it's important because the more you develop, with time, as you develop your project, your code quality tends to decay over time. And that's because you introduce new features to your code that don't quite match the existing architecture, or maybe the requirements have changed and your old code doesn't quite fit those new requirements. And so you have to introduce some maybe not so pure, not so clean architectural decisions. And so because of that, your code tends to decay, the quality of your code tends to decay. And in order to maintain the quality of your code, you have to do continuous maintenance, continuous refactoring. And if your tests raise a lot of false positives, a lot of false alarms, then it will lead to the situation where you lose trust in your tests and you don't perceive them as this safety net that will keep your code operational after refactoring. And because of all that, you become more hesitant to refactor your code. And so why we get false positives? The reason we get false positives in tests is because your tests couple to implementation details as opposed to the end result. So this is coupling your tests to implementation details. It's what produces false alarms in those tests. And let's take a look at some examples. Here, for example, we have these classes. We have the message class that consists of some header, body, and footer. We also have an interface, an iRender interface that takes in a message as an input and then returns a string as a result. So it renders that message into an HTML message. So, and we also have the message renderer class that implements this iRender interface. And this class also implements this render method that takes a message as an argument, and then it delegates the work on pieces, on parts of that message to some sub-renderers, and then aggregates the results and then returns it to the caller. And here, those sub-renderers are the header renderer, the body renderer, and the footer renderer. And here they are. They are quite simple. They just take a message as an input and take some part of that message, wrap it into a tag, into the HTML tag, and return it back. And we also have here, we have a small UML diagram with the message on the right, and then we have the interface, iRender interface, and these 4 classes that implement this iRender interface. So given that code, how can we test this code? The first option here is to check the content of this sub-renderers collection. And if this content, if this collection is correct, if its content is correct, then we can assume that the behavior of this message renderer class is also correct. And here's how the resulting test will look like. So here we instantiate the message renderer instance. Then we take its sub-renderers. We check that the number of those sub-renderers is indeed 3. And then we check that the types of those sub-renderers are also correct. And this is called structural inspection. And it is an anti-pattern. It is an anti-pattern because here this test couples to implementation details of this message renderer. And as a result, this test becomes brittle. And it's brittle because we can modify this message renderer class in any way we want. For example, we can reshuffle the sub-renderers. We can replace one of those sub-renderers with another one. Or we can even remove all those sub-renderers and implement this rendering functionality in the message renderer class itself. And we can do that without affecting the behavior, the observable behavior of this class. But this test will break regardless of whether we did the refactoring correctly. So it will raise alarms, and most of those alarms will be false. And so this is an example of a brittle test, and this test is brittle precisely because it couples to implementation details and not to the end result. And here's another example. So this test, what it does is it reads the content of the message renderer class and then checks that this content is, so to speak, correct. And this example, of course, is quite extreme because you never want to do that. But still, it's not that different from the previous example because both of these tests couple to implementation details, and both of these tests insist on a particular implementation of the system under test. And when you change that implementation, both of these tests will break. Admittedly, of course, this test will break more often than the previous one because here we can, let's say, add a line or even a space, and it will break this test. But still, conceptually, this approach is the same as structural inspection. And this approach is called source code inspection, and it's also an anti-pattern, as you can imagine. So the only way to avoid brittle tests is to bind your tests to the end result and not to implementation details. So what does it mean in the context of our example, in the example of our message renderer class? Instead of checking the sub-renderers collection, the correctness of that collection, we need to check the end result. And the end result here is the string, the HTML string that this render method returns. So here's how the resulting test will look. Here we also instantiate a message renderer instance. We we give it some message as an input, and then we check that the resulting HTML message is correct. And this test is not brittle because it verifies the end result, not implementation details. And if you think about it, the only thing that matters for the end user is how their documents are presented on the screen. They don't care about how exactly the message renderer class implements this functionality. The only thing that matters for them is that this document is represented correctly. And this is what this test targets as well. It targets the behavior of your system as it viewed from the end user's perspective. It doesn't couple to implementation details. And this brings us to this picture that summarizes the previous two examples. So on the left, we have an example of a good test. So a good test is a test that answers the question of, is the end result correct? And that's what we did when we checked the HTML result of the message renderer class. On the right, we have an example of the bad test. So a bad test is a test that answers the question of, is the process correct? So it couples to this process, and when you modify this process, it raises false alarms. All right, so these are the 4 components again: protection against bugs, resilience to refactoring, fast feedback, and maintainability. And let's talk about the relation between the first 2 components, between protection against bugs and resilience to refactoring. So these 2 are related to each other in this way. So they form this metric of test accuracy. And another way to say it is the signal to noise ratio, where the signal is the number of bugs that the test finds, and the noise is the number of false alarms that this test raises when it finds all those bugs. And the first component, the protection against bugs component, is responsible for the signal part. And the second component, the resilience to refactoring component, is responsible for the noise part. Basically, the first component tells you how good your test is at finding bugs. And the second component tells you how good your test is at not raising false alarms. And both of these metrics are critically important. And that's because even if your test doesn't raise any false alarms, it doesn't produce any noise, if it cannot find any bugs, if it doesn't generate signal, then this test is worthless. Well, that's pretty obvious, because the only reason why you write those tests is to have them find bugs for you, reveal bugs. But the opposite is also true. Even if your test is capable of finding of any bugs in your code, if it does that with a lot of noise, then its value, its accuracy also gets to 0, to almost 0. And that's because if your test generates a lot of noise, it just is not capable. You're not capable of differentiating between true noise and false noise. All that noise is lost basically in all that irrelevant information that your test generates. So another way to describe these 2 metrics, protection against bugs and resilience to refactoring, is as you can say that protection against bugs tells you how good your test at indicating the presence of bugs, and resilience to refactoring tells you how good your test is at indicating the absence of bugs. And as I said, both of these metrics are critically important. So here are the 4 components again. And in my experience, a lot of problems with unit tests in a lot of projects stem from this tendency of developers, of people, to not pay proper attention to this second component, to the second metric, resilience to refactoring. So I see quite often that people pay proper attention to protection against bugs, to fast feedback, to maintainability, but they don't pay proper attention to resilience to refactoring. And that's, as I said, is the reason of a lot of problems with a lot of unit tests. And why that is, why people don't pay proper attention to resilience to refactoring. We can plot this diagram with with how false negatives and how false positives affect your project with the duration of that project. So false negative is when your test says that there is no bug, but in fact there is a bug. So basically when your test cannot find a bug, cannot reveal it. And false positives are the opposite of that. It's when your test says that there is a bug, but in fact there is no bugs in your code. And these lines show how these two phenomena affect your project over time. So basically, your false negatives are important pretty much from the very beginning. And that's because you do want your tests to reveal bugs pretty much also from the very beginning of your project, because that's basically the reason why you are writing your tests, so that they will reveal any bugs in your code. But the importance of false positives is not as immediate. It grows over time. It's not that important from the beginning of your project. And that's because the importance of refactoring is also not immediate for your project. So when you just begin your project, the importance of refactoring is not important because the code is shiny, it's clean, it's clear. You haven't the importance of false positive rises with it. And so this is why people tend to pay proper attention to false negatives. It means that when the tests cannot find you bugs, but not that many people pay proper attention to false positives. It's when your tests say that there is a bug, but there is no bugs in the reality. So here are the 4 components again. And also, it's interesting to discuss how the first 3 components relate to each other. And they relate in an interesting way. They relate such that you cannot maximize all those 3 components. You can only maximize 2 of them at the expense of the 3rd one. And let's take some examples. So the first example is end-to-end tests. They are sometimes called functional tests, and that are tests that verify your system end-to-end. They verify not just your code, but also the code your system integrates with, such as the database, some payments services, and so on and so forth. And such tests provide you with the best protection against bugs, because such tests go through a lot of code, not just your code, but also the code that your code integrates with. Also, they provide you with the best resilience to refactoring. And that's because such tests are the most distant from implementation details of your code. They verify your system from the end user's perspective. They don't care about implementation details at all. And but the drawback of these tests is that they are quite slow. And you cannot cover all your application with just end-to-end tests because of that. They are also not quite maintainable, but that's a different topic. And if we draw our first 3 metrics components as these circles, then we can put end-to-end tests in the intersection between resilience to refactoring and protection against bugs. So they provide you with good resilience to refactoring, with good protection against bugs, but they lack speed. They don't have fast feedback. They don't provide you with fast feedback. We can also come up with the second example, and that is the trivial tests. Trivial tests are tests that cover some trivial functionality. Here, for example, you can see on the left, the user class with the simple name property. That property just have a getter and setter, and that's it. And on the right, we have a test that covers this name property. It assigns this property some string and then checks that the string is correct. The benefits of this test is that it is quite fast, and it also provides you with good resilience to refactoring, but it doesn't give you protection against bugs, simply because there is not much room for bugs in the code on the left, because it's quite simple, and there's not much point in covering that code. And so if we show our diagram again, we can put trivial tests in the intersection between these two components. They have good resilience to refactoring, fast feedback, but they don't give you protection against bugs. And the third bucket here would be fragile tests. So we already discussed an example of those fragile tests in the beginning, and that was when we checked the message render by checking the collection of subrenderers. And this is another example. So here on the left, we have a user repository that has some method for getting the user by the ID. And when you execute that method, it puts the last executed SQL in this property called last executed SQL. And on the right, we have the test that checks this repository. So what it does is it tries to just query some user and then checks that the SQL this repository generates is correct. And so this test is good in the sense that it is fast. It also, this test also gives you good protection against bugs. Why good? It's because, well, you as a developer may make a mistake in that SQL. And if you do that, this test will reveal that mistake. It will tell you it will break, and therefore it will say you will be able to address this. Well, you basically will be able to notice that bug. But the problem with this test is that it has bad resilience to refactoring. And that's because it couples to implementation details of this repository. So in the middle, you can see the 4 alternatives to this SQL that are equally good from implementation standpoint. So we can change our implementation, our SQL in the user repository to any of these 4 options. But if we do that, the test will break, and it will break regardless of whether we modified the SQL correctly or not. And so that's why this test is fragile. It's because it doesn't check the end result, it checks the implementation details here. And we can put fragile tests in this intersection between protection against bugs, fast feedback, but no resilience to refactoring. And this ideal in the intersection between all 3 components, unfortunately, this ideal is unreachable. You cannot have all 3 components maximized here because, as I said, you can only maximize 2 of them at the expense of the 3rd one. But still, even though we cannot achieve this ideal, we can approximate our tests pretty closely to that ideal. And let's discuss how to do that. So here we discussed how to measure the effectiveness of a test. Again, for that, we need to use the 4 components. And now let's talk about how to actually write effective tests. To write effective unit tests, and not just unit, but any tests, any automated tests, you will have to refactor the underlying code. And unfortunately, there is no way to go around that because your unit tests are coupled, they are inherently coupled to your production code. And so to achieve efficiency in unit testing, you will need to work on your production code base as well. We can plot any piece of code using these 2 dimensions. So we can estimate any piece of code with these 2 dimensions, complexity and importance on one hand, and the number of collaborators on the other. Complexity and importance, so if some piece of code is complex or importance from the business perspective, covering such code gives you the best return on your investment, because these, as I said previously, the most critical bugs are usually in either business logic or some complex functionality. And covering that business logic or functionality gives you the best protection against bugs. So this is the type of code that you need to cover the most. On the other hand, we have this number of collaborators metric, and collaborator is a dependency that is mutable, that can be changed. Now, so for example, if you test a user class and this user class has a dependency on a company, and this company is mutable, then this company will become a collaborator for this user class. And so if your system under test has a lot of collaborators, then the resulting test will have high maintenance costs. And that's because they will have to set up those collaborators in order for your test to work properly. And then maybe even check the state of those collaborators and how your system under test communicates with those collaborators. And it also not only the number of collaborators that matters here, but also the type of those collaborators. If your collaborator is in process, that's one thing. But if it's out of process, if it's an out of process dependency, then you will also have to work with the network issues, potential network issues, work with the dependency itself, keep it operational, and so on and so forth. And so the fewer the number of collaborators, the better your tests are in terms of maintenance costs, the cheaper it is to maintain those tests. And so if we take these two metrics, these two dimensions, and plot it on a diagram, we will get this 2 and 2 quadrant, 2 and 2 square with 4 quadrants. So the left upper square is domain model and algorithms. They have the most complexity or domain significance, but on the other hand, they have few collaborators. Ideally, they shouldn't have those collaborators at all. On the bottom left, we have trivial code, and that's code that is simple, for example, one-line properties or constructors that don't do anything other than assigning some arguments to internal fields of the class. On the right, on the bottom right, we have controllers. Controllers are classes that don't do important or complex work on their own, but they orchestrate this work between different components of your system, usually between your domain model and out-of-process dependencies, such as the database. And on the upper right quadrant, we have the overcomplicated code. And that's a good example here is a fat controller anti-pattern. It's a controller that doesn't delegate the work anywhere, but does all that work itself. And this is the type of code that brings the most pain to the project, so to speak, from the unit testing perspective. And that's because it's risky to keep this type of code untested, but it's also quite expensive to test this code because it has a lot of collaborators. So from the unit testing perspective, the testing of domain model and algorithms provides you with the best return on your effort, because the resulting tests are valuable and they are cheap. They are valuable because they test the complex or important functionality, and they are cheap because that functionality doesn't have a lot of collaborators. Trivial code, you shouldn't just test it at all because the resulting tests, they don't have enough value to justify their existence. So you just need to skip those tests altogether. And for controllers, you do need to test them, but you can do that with a much smaller set of integration tests. You don't need to test them that thoroughly. But as I said, the overcomplicated code is the problematic code because, as I said, it's risky to keep it without testing, but it's expensive to cover it extensively with tests. So what you need to do in order to unit test effectively is you need to refactor this overcomplicated code and move it either to the quadrant of domain model and algorithms or to the quadrant of controllers. So basically you need to split this overcomplicated code into controllers and algorithms. And this approach is called humble object design pattern. And this pattern says that if you have this overcomplicated code, and this code is overcomplicated because your logic is intertwined with the hard-to-test dependency. If you have such a code, you need to split that code into these two separate components, into the logic component and into this hard-to-test dependency. And you can glue these two pieces together using a new third component, which is called humble object. That's basically the controller that we saw in this diagram. So, and after this split, you can unit test the logic components separately from the hard-to-test dependency, and your tests will not be as painful to write as they would otherwise. So here on this diagram, the humble object is the controller, and your integration tests will then cover this humble object or the controller, and your unit tests will cover the logic part of the split. And there's a good metaphor for this split and this. So the guideline here is that the more complex or the more important your code is, the fewer dependencies this code should have. And this is the metaphor that you can apply to visualize this guideline. So basically, your code can be either wide or tall, but it shouldn't be both at the same time. And here we can see the controllers that I represented as a wide but short box. And it is wide because it has a lot of collaborators, and it's short because the controller itself is not that complex. It delegates the complexity out. And on the right, we have the domain layer or the algorithms that are tall, and they are tall because they are complicated, they are complex, but they are thin because they don't work with a lot of collaborators. And so that's the guideline, the visualization of that guideline. And the humble object pattern itself, there's nothing new about that pattern because a lot of existing patterns in software development, they implement this approach of this humble object design pattern. For example, we can say that the MVC design pattern is basically the same as the humble object design pattern because it also follows this principle where you separate your logic or model from the hard-to-test dependency or view. And after that separation, you will be able to test that model, that logic part, independently from that hard-to-test dependency, from the view. And the controller remains as this humble object that orchestrates the work between the model and the view. And so in the result, we will have this picture where on the one hand, we have unit tests that cover the domain model and the algorithms part, and we have integration tests that cover the controllers part. And we shouldn't cover trivial code at all, and we shouldn't have overcomplicated code. We should refactor that code into either domain model and algorithms or the controllers part. And we can also look at the widely known test pyramid from this 4 components perspective. So the test pyramid is, I think everyone knows about that, but just to reiterate, it's the ratio, it shows the ratio between different types of tests in your test suite. Basically, the unit tests, the number of unit tests is the largest, the number of end-to-end tests is the smallest, and the regression tests are somewhere in the middle. And we can look at this test pyramid from our new perspective, from the perspective of the 4 components. The higher you get on this pyramid, the more you get in terms of protection against bugs and resilience to refactoring. But the lower you get on that pyramid, the faster your tests becomes and the more maintainable they become because you don't have to work with a lot of out-of-process dependencies. So so we discussed how to measure the effectiveness of a test. Then we discussed how to apply that knowledge in practice. and let's discuss the mocking topic, the topic of mocks. So mocks are, well, they are constructs that help you to test your system under test. So basically, the benefit of using mocks is that you can isolate the system under test from its dependencies and test that system under test in isolation so that you don't have to recreate all those dependencies in your tests. And there could be a lot of those dependencies, and so this approach may become quite useful. So let's discuss when you should and when you shouldn't use mocks in tests. For that, we need to discuss different types of dependencies in code. So dependencies can be mutable and they can also be immutable. So mutable dependencies are the collaborators that we discussed previously. On the other hand, in turn, mutable dependencies can be either out of process or they can be in process. So out of process dependencies are dependencies such as database, file system, and so on. And in process mutable dependencies are just some entities. For example, as I said, if you test a user class and this user class has a dependency on a company class, then this company becomes a mutable in process dependency. That's given that this company doesn't reach out to any out of process dependencies and so on. And also immutable dependencies also can be broken down into out of process dependencies and in process dependencies. So an example of out of process immutable dependency is some read-only API service where you can read some data, but you cannot modify that data. And an example of in process immutable dependency is a value object or just value. So the simplest example is just number 5. When you put number 5 as an argument to some function, you cannot modify that number 5 because it is immutable. And so there are two schools of thought here in terms of when it comes to mocking. The first school is London, and the second school is the classical school. They are also called, so the London school is also called mockist, and the classical school, well, we'll just call them the London school and the classical school. And the difference between them is that the London school advocates for replacing all mutable dependencies with mocks in tests, whereas the classical school advocates for replacing only out of process mutable dependencies with mocks in tests. And both of these schools are incorrect in their treatment of mocks. And let's discuss why that is. So the London school is incorrect because not all communications with, communications with not all dependencies are observable behavior. So for example, here we can represent our application as this hexagon, which has some third-party client, third-party system, and also it has some downstream dependencies such as a message bus. So when your system calls, when a third-party system calls your system, and when your system calls a message bus, so basically the communications between external systems here are part of the observable behavior of your system. But the communication between classes inside your system are not part of that observable behavior, because it doesn't really matter for the end user, for the client, how exactly your classes communicate when they invoke some method in your system, when they call some API on your system. And those internal communications are implementation details. And if you couple your tests to those implementation details with mocks, then you will have fragile tests. And that's the second component that we discussed previously. So basically, you will not have good resilience to refactoring, and with any change of that communication pattern, your tests will break. And that's why the London school is incorrect. You shouldn't replace in-process mutable dependencies with mocks. So let's now discuss why the classical school is incorrect. So just as the communication between classes inside your system are implementation details, also not all communications with out-of-process dependencies are observable behavior. So some of them are also implementation details. And a good example here is the application database that is only accessible by your application. Communication with that database also is an implementation detail. And well, to describe why, we need to discuss why, we need to discuss the topic of backward compatibility. So backward compatibility between application is, it's when you have to maintain communication pattern with the out-of-process dependencies. So let's say you develop an application and some other application integrates with your application using a message bus. And regardless of the refactorings that you make inside your system, you should preserve the type and the content and the structure of the messages that you put on the bus. So you basically cannot change the format of those messages, because if you do that, then you will break backward compatibility. Those other applications that integrate with your application, they will not be able to recognize those messages and they will not be able to communicate with your application anymore. And that's in turn stems, this requirement of backward compatibility stems from this inability of deploying those applications together. So let's say if these two applications, your application and this downstream application, if they are developed by different people in your team, not in your team, but in your company, let's say by different teams, and they might have different deployment schedules. And because of that, you cannot deploy them together. And that's why you have to maintain backward compatibility so that even old versions of that application will be able to talk to your application. And mocks are great for that. They are great to for ensuring that the communication pattern between your application and those other applications remain intact, to ensure that you don't break that communication, you don't break those other applications. But database is not accessible to external applications. And because of that, you don't need to maintain backward compatibility with that application database. And so communication with such out-of-process dependencies becomes an implementation detail. And that's because external applications do not see this, your database directly. Your system and that database becomes effectively becomes one system. You can modify anything in that database and it will not affect the external systems in any way. For example, you can split a table into two, or you can even replace a relational database with some NoSQL solution altogether. And you can do that in a way that will not affect your clients, as long as you do that without changing the observable behavior of your system. And so because of that, communications with the database or with other such dependencies become implementation details, and you shouldn't couple your tests to those implementation details, otherwise they will become fragile as well. And so to have this, well, to discuss this guideline, we need to subdivide our out-of-process dependencies further into managed dependencies and unmanaged dependencies. Managed dependencies are the dependencies that are not visible to the outside world. That's typical examples here are application database and the file system. So as long as other applications cannot reach out to your database directly, and they can only do that through your application becomes a proxy, so to speak. This dependency is a managed dependency, and communications with that dependency becomes an implementation detail. On the other hand, unmanaged dependencies such as the message bus and SMTP service, it's dependencies where that are visible to other applications. So the side effects that you incur in those dependencies, they become visible to outside applications. And only these type of out-of-process dependencies should be mocked out. So only unmanaged dependencies should be replaced by mocks in your tests. Because as I said, mocks are great for maintaining backward compatibility. They are great because they allow you to set in stone, to solidify the communication pattern between your application and unmanaged dependencies. And that's exactly what you want with unmanaged dependencies, to maintain backward compatibility. But it's the exact opposite of what you want with managed dependencies, because you don't have to maintain backward compatibility with them. All right, that's basically all I have. That's again my unit testing book, and we can discuss some questions.
Yeah, thank you, Vladimir. We have plenty of questions. Let's see, not plenty, but some questions on the chat. Maybe we can start by them. Let's go back. Let's go back in time. Uploaded. Yeah. So we had one question regarding test approaches. Do you need more further explanation, Michael or Mikhail? I don't know. The question was, I learned recently that there are 2 TDD approaches, Chicago and London. My question was when to use it. So I think it has answered the rest. Yeah.
Yeah, that's basically the last part when we discussed mocks. As I said, the London school, it makes an emphasis on mocking of all dependencies other than immutable dependencies. And the Chicago school or the classical school, or Detroit school, it's about not using mocks that often. But in my opinion, my personal opinion, it also is incorrect in terms of those managed out of process dependencies.
Okay, thank you. We have another one. There's some new questions. Okay, so we have a question regarding AI and testing. Maybe Julian, you can unmute and ask yourself the question, please. I don't know if you are still there. It would be easier, I think. Yeah. Could you unmute? Okay. I will do it for you. So there is a question. If you know tools like Ponycode, have you already tried it? And it's basically AI-powered extension pack that generates unit tests for us. What is your take on it? Don't choose or use it.
Well, I'm not familiar with this particular tool or any AI-powered tools, to be honest. But generally, it looks like it's similar to. We as an industry had a lot of such tools, similar tools, where you can generate your tests given some code. And my opinion on that is pretty much the same as code generation. Well, the short version is that you shouldn't do that, because these tools, they don't have context for your particular project, and they don't know what is and what isn't important to test in that project. It's basically the same as generating code for your business logic or for your domain model, because it's also useless, because it's the most important part of your application, and only by communicating with the domain experts and with the business, you can figure out which of those, how exactly should you build your business logic and your domain logic. And so in order to configure this AI or some other tool to build your domain logic precisely, you will have to expend as much effort as building the domain logic itself. And so it doesn't really worth it. It's just an overhead, whereas you can skip that overhead and just build that domain model yourself. And with unit testing, it's the same thing. Basically, the tool doesn't know which parts of code are important, which parts constitute implementation details, which not. You have to have input from the business and from the end user to understand which parts of your behavior of your application constitute the observable behavior, and which of them you should target with your tests. And so, yeah, that's unless those AI tools become as smart as people, I think in all other cases, you wouldn't be able to replicate the quality of your tests with them.
Okay, thanks. So a question from Alexander. Don't hesitate to unmute to add something on the question. So he said, Vlad, do you plan a book to cover integration tests in more detail? How would you write integration tests for an ASP.NET MVC5 web app written in C#, for example, with huge fat controllers, but don't delegate anything to anyone.
Well, I tried to cover this topic in the third part of the book. That's basically fully devoted to integration testing, including how to test it with mocks and how to test the database directly. I really don't have anything other than that to say. It's about third, I think, of my book is devoted to this topic. If you have some specific questions, let's discuss, because if I didn't cover some interesting topics, then I might cover them maybe in the article format or some other way.
Yes, Vladimir, my question was about when controllers intermix HTTP request codes and database CRUD operations and error handling, exception handling, all of that stuff, which is why I call them fat. And I saw example code from your book and I downloaded the code that comes with it, but your examples are different from what I see in production.
Right,
Our architecture is not that
basically
plain.
There are a lot of layers on top of that logic that you want to test as well, such as exception handling, maybe routing and so on, right?
Basically, when a user interacts with a page, they just see a page, but it's not end-to-end tests I'm talking about. It's just how to cover those controllers logic.
Right. Yeah, that's a good topic to write about.
Or maybe how to improve architecture so we don't have that problem. So we don't have to test our controllers.
Well, basically, humble object is the go-to pattern in these situations. You have to extract your domain logic out of those fat controllers. That's the first and the easiest step usually to do, and cover that logic with unit tests and only cover the remaining part with integration tests. Another thing is usually when you have controllers, you don't just have controllers as like, well, as I showed it in the book, where you have the orchestration between the domain model and with the database. You also have some additional layers on top, for example, some middleware or some exception handling or routing. And so a lot of that stuff are piled on top of that logic, and you need to test that logic, that code somehow as well. So here I would recommend, and that's the middleware that is invoked for each controller method execution. So basically, when the external client calls your application, that call goes through all that middleware, and only then gets to the controller that does the orchestration between the domain logic and the database, let's say. So to cover those middleware, those layers, I would recommend that you just write maybe one or two tests that go through all those layers and keep it at that, and just test the controllers with an extensive set of integration tests, but don't test all those layers on top of those controllers with each of those tests. So I'm not sure if it answers your question, but that's what I think is missing in the book. But if you're talking about how to separate, well, the humble object design pattern is the only way to do that, in my opinion.
Yep.
Thank you.
Oh, yeah, we have a question from Jacek. I don't know how to pronounce it. Sorry for that. It has been answered by Guillaume. The question was, are really unit tests related to a class or a function? Could you imagine writing unit tests that test actually a few classes together, because the algorithm is a bit more complex and is split across multiple classes?
Right. So there is this guideline of covering, so where one unit test should cover just one piece of code, such as a class, for example. And that's, I think, is anti-pattern. You shouldn't approach it this way, because your test should target a single piece of behavior. They shouldn't target a piece of code. And a behavior, a single piece of behavior, it can take just one class, maybe it can take multiple classes. It doesn't matter. What matters, what should matter for your code, for your tests, is that it's a single cohesive piece of behavior. And that's because your tests should approach testing your system, even unit tests, should approach your system, testing your system from the end user perspective. And for the end user, it doesn't really matter how many classes you create to implement some particular piece of behavior. The only things that matters, the only thing that matters is the observable behavior of all that code. And so because of that, it shouldn't really matter how much code it takes to implement that piece of functionality, that piece of behavior. The only thing that should matter is that it's a single piece of behavior, and you shouldn't test more than one. And that's of course contextual from project to project. You cannot just say that this is one piece of behavior, this is another. You should have some domain knowledge in order to differentiate different pieces of behavior.
Okay, thanks. So I understand it that I should be actually testing some kind of an API that a class or a module package, whatever it is, offers to the outside world or maybe to other parts of the system. But then how do you differentiate unit tests from integration tests? We are, I think, still talking about those, and we focus, okay, this is a unit test, this is an integration test. What I do really care about is that I'm testing a functionality.
Right. So basically, you need to view your code, your functionality on two layers. The first layer is the domain model. I don't have this slide here, but basically you can represent it as an onion, where in the center of that onion is the domain model or the business logic. And on top of that, you have the application layer. And the domain layer is the abstraction for the logic of your application. It's an abstraction because it doesn't actually talk to any out-of-process dependencies, to the database, and so on. It represents that domain logic or domain knowledge. And so this is one level. And here on this diagram, it is showed as this domain model and algorithms quadrant. And this is what you need to cover with unit tests. And when you put application layer on top of your domain model, you will get basically your full application or almost full application. So you basically put controllers on top of that domain model, and those controllers orchestrate your domain model with out-of-process dependencies. And those controllers are what you need to cover with integration tests. And that's the number of integration tests will be smaller than the number of unit tests, because you should cover as thoroughly as possible, should cover the domain model as thoroughly as possible, all the edge cases and so on. And with controllers, because you already covered the abstraction, the domain layer with the extensive set of tests. For the controllers, you can just write a smaller set of tests that cover some let's say, happy path and maybe some edge cases that cannot be covered by unit tests. So does that answer your question? And your unit tests, if we're talking about testing multiple classes, those unit tests still can test multiple classes, multiple domain classes or business logic classes. It's just those several classes must implement one single cohesive piece of behavior. You shouldn't test just one class because it's a class, and you should see it from the perspective of the end user. And if multiple domain classes implement the same piece of functionality, then you should test them together. A good example here would be something like an order class that contains multiple order lines. And so what you have here is the order class itself, and then the other class is the order line class. And you shouldn't really replace order lines with mocks here in order to test the order in isolation from those lines. You should test them together because it's a cohesive piece of functionality, and you shouldn't split it.
That just confirms my thoughts about the testing. Thanks.
Okay, so it's 6:40. I think we need to close here. Do you have really one question that you need to you need to answer? If you have one question that you really need, you won't sleep if you haven't the answer from Vladimir, please ask it now. Otherwise, we will close the meetup here. So don't hesitate. Unmute. One last question if you have one. No one?
Is there just one question, Marco? Is there a possible way to submit questions to offline?
Yeah, sure. You can, if you can put my email address somewhere.
Yeah, because I have another questions, but I just don't want to rush now.
Yeah. Okay.
Yeah,
okay.
Thanks. Yeah. So you shared on the chat. Where is it?
Let me put it here.
Yep. Perfect. All is good.
Okay. Okay, great.
Thanks.
Thank you. Thank you all. Thank you, Vladimir. Thank you for your time, for your work, for your great presentation. I hope you've learned a lot of stuff and you will apply it in your day-to-day and share it. And don't hesitate. Please read the book from Vladimir. It's really, there are plenty of good learning from it. Really. Thanks again.
Thanks everyone. Thanks for inviting me, and thanks to you all for coming.
Yeah.
Thank you. Thank you, Vladimir.
Thank you. Bye.
Yeah. Thank you.
Good evening. Bye-bye.
Have a good evening. Yeah. Thanks.